hard as diamond, as soft as graphite. Carbon, the basis of organic chemistry. Combined in nature with hydrogen and sometimes oxygen, it gives us things as different as silk, rubber, and oil. Now, using the same elements, the organic chemist synthesizes a whole range of new materials. Plastics, resins, textiles, and detergents. All detergents incorporate a hydrocarbon chain. The molecule has a water-hating or hydrophobic tail and a water-loving or hydrophilic head. This is its fundamental character. In the surface of water, the hydrophobic tails protrude between the water molecules, reducing surface tension. The earliest detergent, made from animal and vegetable fats, was soap. Sodium palmitate is a typical soap molecule. It has a hydrocarbon tail and a sodium carboxyl head. But animal and vegetable fats are in such demand for food that alternative raw materials for detergents had to be found. In 1831, a French chemist, Edmond Frémy, poured sulfuric acid into olive oil. After the solution had been neutralized, it had a distinctive soapy appearance. This was the first step which led a century later to the production of modern soapless detergents. To synthesize a soapless detergent, the first requirement is a hydrocarbon chain. Petroleum was known to be a source from which a hydrocarbon chain could be obtained. A byproduct of petroleum, alkylbenzene, a compound of a hydrocarbon chain and benzene, became available in commercial quantities. Alkylbenzene is not a simple compound. It is a mixture in which the hydrocarbon chain varies to some extent, but it has an average length, most suited to soapless detergents, of 12 carbons. To this chain is first added a benzene ring. Two hydrogen atoms are lost, and the resulting molecule has a total of 18 carbons in the whole hydrophobic chain. Now a head group, SO3Na, must be added. This is more easily put onto a benzene ring than onto a hydrocarbon chain. How is this reaction, called sulphonation, carried out in a laboratory experiment? Alkylbenzene hydrocarbon is poured into a flask and cooled. A thermometer, a stirrer, and a separating funnel are inserted. The temperature must now be brought down to 10 degrees centigrade. Oleum, a solution of sulfur trioxide in sulfuric acid, is measured out and poured into the separating funnel. Stirring is started before the addition of the oleum, since the reaction mixture must be stirred vigorously throughout. As the oleum is added, heat is generated. The rate of flow must therefore be adjusted so that the temperature does not rise too quickly. It should not go above 56 degrees centigrade. An excessive rise would cause undue discoloration and a low yield. Ice must be added from time to time to control the rise in temperature. The reaction continues for 30 minutes after the oleum has been added, and the mixture becomes darker. As the heat generation slows down, small quantities of hot water must be added to keep the temperature steady at 55 degrees centigrade, plus or minus 1 degree. If it were to fall, the mixture would become thick and difficult to mix, and again there would be a low yield. At the end of 30 minutes, the sulphonation reaction is complete. The warm water is then siphoned off. The mixture is now cooled to a normal room temperature, 20 degrees centigrade. The product of sulphonation is called alkylbenzene sulphonic acid. It is not yet a detergent. It must now be neutralized. For neutralization, a small quantity of crushed ice is measured into a beaker, which is placed in a bath also containing ice. Caustic soda is dissolved in water. The required quantity of alkylbenzene sulphonic acid is measured. The caustic soda is then added to the crushed ice, and the sulphonic acid is poured in as quickly as possible. There is an immediate rise in the temperature, which must be kept below 50 degrees centigrade. The mixture must be checked. If too alkali, more sulphonic acid must be added. And if too acid, more caustic soda. The result is alkylbenzene sulphonate. A detergent molecule has been obtained by laboratory experiment. The significant change to the hydrocarbon molecule has been the replacement of one benzene hydrogen by the head group SO3Na. The techniques for the large-scale production of alkylbenzene sulphonate look very different from the bench experiment, but the chemical reactions are the same. Sulphonation and neutralisation in bulk are continuous. Oleum and alkylbenzene being brought together in an enclosed process at a rate which keeps the reaction under control. The excess heat energy must be removed before it can damage the product, and there must be the same safety of handling as in the laboratory. The neutral alkylbenzene sulphonate which is produced is a spearhead from which is made a whole range of soapless detergent products. It is a surfactant as made in the bench experiment. It will help in wetting and removal of grease, but other constituents must be added according to its domestic use. The effect of some of these can be demonstrated. If a single fibre of a textile is covered with dirt particles and plain water allowed to flow across, no visible reaction occurs. But the addition of phosphates, which form soluble ions and soften the water, brings the particles streaming from the surface of the fibre. The dirt removed from the fibre must then be kept in suspension, prevented from resettling. So a dirt suspending agent is added. Dip a clean cloth in a fine dispersion of carbon in hard water. Rinse the cloth in plain water and it can be seen that many of the carbon particles have resettled and the cloth looks grey. Dip another piece of cloth in a solution containing the dirt suspending agent, and it will receive a strongly repulsive ionic charge. Now dip it in the suspension of carbon particles and rinse it. It can be seen that the particles have been repelled from the treated half of the cloth. Fluorescent agents, the effect of which can be demonstrated under ultraviolet light, are added to compensate for the natural discoloration of all fabrics through age. Stains, such as the juice of black currants, can be removed by the addition of a bleach. The bleaching agent is sodium perborate. When the cloth is dipped into a hot solution, the action is very rapid. When the detergent is to be used as a powder, there is another important factor to consider. Although alkylbenzene sulphonate paste can be dried, it is strongly hygroscopic. It will become paste-like again in a very short time. And for this reason, anhydrous sodium sulphate and sodium silicate are added, so that when dried out, it will remain a free-flowing powder. In commercial production, all those constituents which do not decompose with heat are mixed with the alkylbenzene sulphonate before drying. The mixture is pumped to the top of a drying tower. The fine spray of paste dries in a hot chamber and falls to the base as a powder. So the essential requirement in the synthesis of a detergent is a hydrocarbon chain to which can be added a water-loving head. Thus, alkylbenzene, a byproduct of petroleum, and oleum, a solution of sulfur trioxide and sulfuric acid, are brought together. This is the process of sulphonation. The result is alkylbenzene sulfonic acid. The sulfonic acid is then neutralized by adding it to caustic soda. This produces a detergent molecule, alkylbenzene sulphonate, which is formulated with other constituents for domestic use. By the study of hydrocarbons, the organic chemist synthesizes a whole range of new materials to meet the needs of the modern world.